Okay, we're going to start Gauss's law. I thought I had that shot.
You finish your equations?
Oh, there's a little bit here. I'll grab some. So Gauss's law, before I start that, because it involves dot products, I would like to just remind us of the dot product of two vectors. So if you have the dot product of vectors A and B, it's equal to the magnitude of the vector A times the magnitude of vector B times the cosine of the angle between them, right? The angle between the two vectors. Yes? That's the dot product of two vectors. Okay. Dot product could be plus, minus, or zero. So if this is A and this is B, and this is the angle between them, versus this is A, this is B, versus A, B, and the angle between them. In this case, A dot B is going to be positive or negative? Yeah, greater than zero because the angle cosine of theta would be positive. In here? Yeah. And here? Okay, it would be less than zero. Okay. So the dot product here is going to be less than zero. All right? Now, here's my bucket, and we're going to talk about the concept of flux, and it's helpful to talk about it in terms of rain. Okay, so imagine it's raining, and usually it rains from top to bottom, right? Straight down. And if I want to collect the maximum amount of rain, I want to orient my bucket this way. So the rain will enter my bucket. And I can think of the area of the bucket, this area, as pointing upward. This, and the rain is coming down, and so I get the maximum amount of rain entered. If I start to orient my area this way, I will get, it's less optimal, right? And when it's this way, when it's just horizontal, how much do I get? Zero. So they're perpendicular, yes. You can think of the rain coming down, and then the area is pointing this way, none of it enters. Okay? So if it's entering into the bucket, I can think of the rain that enters, that's the flux in, that would be negative flux. If it's coming in, it would be negative because the area is pointing up. In what direction is the rain pointing? Down. Down. Yeah. Rain is down, and then the area is up. I think you got the idea. Okay. So in that case, the dot product is negative. If I open a hole in the bucket, then it will start leaking, and the area in that case of the bucket in here, the down, the area of the bottom points down, and the rain will be leaking down. In this case, the flux will be positive, so it's leaving. If it's entering, it will be considered negative. If it's leaving, it's considered positive. Okay. Just because of. Now, we have two types of surfaces. There is what's called an open surface and a closed surface. This is an open surface. It doesn't have, where is the inside of this? Yeah. This is a closed surface. Yeah, because I know where, if I'm inside or if I'm outside. Okay. We'll come back to that. Gauss's law talks about closed surfaces, but for here, we're talking, let's just introduce the concept of that. Very similar to rain. Now imagine the ceiling is positively charged and the floor is negatively charged. You will have an electric field. In what direction is the electric field going to be? The top is plus, the bottom is minus. Electric field goes from plus to minus. So electric field is down, right? So it's raining electric field and it's downward. And so again, here is my surface. If I want, let's get rid of the bucket. Here is my surface now. If I want maximum electric field through this cardboard, I want it to be this way. If my cardboard is like this, then how much field do I get through it? Zero. It will just pass by, but the area is this way, the field is down, so I get nothing. So no flux. Okay? So the concept of flux is basically this. The stuff that I want to get in comes the area. So in the case of the electric field, it's the electric field. And then what I want, and then the area is made. Yeah? Yeah. Yeah, the net flux will be good. We will worry about that in a little bit. Yeah. And that with Gauss's law, that we need to worry about that. But for now, let's just introduce the flux and then we'll get to it. Okay? So here's the concept of flux. Electric flux. We'll call it electric flux because we're specifically talking about flux that's due to electric field. Electric flux. In a few chapters, there is a similar concept, but it's called magnetic flux. Magnetic flux. But today, it's just electric flux. Sometimes I would just say flux because it's clear we're not talking about magnetic flux. We're talking about electric flux. So people will have this symbol. This is V for flux. V for flux. And sometimes they will put E to mean electric flux. I will just put this. Okay? So this is the electric flux. And its definition is basically this. The integral of the electric field dotted with the area, like the element of area, dA, E dot dA. That's the general definition of flux. Technically, it's a double integral because area would have dx and dy, but in reality, when we apply Gauss's law, we're really avoiding to do any integration. We will not do a double integral, we will not even do a single integral. It's going to just be, we're going to reduce it to be just a constant. Okay? And that's the goal, to avoid doing much work. So this is Gauss's law. I'm sorry, this is not Gauss. This is the definition of flux. Right? V is flux. And very often, this gets reduced to this. I'll put here very often. We'll see under what condition. Basically when the electric field is constant. Very often it looks like this. This becomes just electric field dotted with area, which is just electric field times area times the cosine of the angle between. This is, in general, it's this. In many cases, it just becomes this simpler form. Okay? In many cases, it just becomes this simpler form. And I plan to do 4 or 5 examples on this to make sure you understand this equation. Okay? So please bear with me and pay attention to it. Okay? So we're going to use this, okay? So I have a few examples here on the board below. Example 1. Ignore example 2 for a moment. We're going to come back to it in a second, after we finish the example. Okay? So we have an area here. And they're telling you, here's the area. This is the area, and they're telling you that the area is pointing to the right. The area is pointing to the right. How do we know? Well, they told me. They said the area, assume, is pointing to the right. This is n hat, is the unit normal from the area. So this is the area. The area pointing to the right. We have a positive charge here, and we have a negative charge here. And the question is the flux through this surface, is it going to be overall positive, overall 0, overall negative, or maybe we can't even tell. I give you 3 options, so we should be able to tell. So it would be, you said why would it be negative? Good, so you're saying this. The area is pointing this way. Okay? The area points left. In what direction is the electric field due to the positive charge? Right. Somehow to the right. right? Like this. What's the dot product of vectors they point right and a vector that points left? Negative. How about the electric field due to the negative charges? In what direction does it point? Also, it points toward the minus charge, right? So notice all the fields, they have a component to the right. But the area only points left. Electric flux is basically EA cosine theta. So the area and the electric field are, they make an angle that's greater than 90. Therefore, negative. So the flux would be less than zero. The two vectors are, one is pointed right and one is left. The dot product would be overall negative. So that's the first conceptual question. Okay. We're going to go to the next example 2. Example 2, we're more specific. You have 4 cases, and for each case, they want you to find the electric flux in each case. Okay? They want us to find the electric flux in each case. Case 1, the electric field points in the x direction, and the area points in what direction? Leftward. I know I drew a line here, but think of this line is the area is like this, okay? It's meant to be some area this way. So the area points left, and the electric field points right. So what do you think the flux is going to be? Positive, negative, or zero? Zero? Why would it be zero?
Negative.
Or negative? Yeah, they're anti-parallel, so it's going to be negative. Let's use this equation to find it. I'm going to show you how this equation can be applied to here. The definition of flux can be applied to here. It's not really needed, not absolutely necessary, but I want, because we're doing practice. The flux, let's do, I'll call it flux 1, because it's the flux in the first case, it's case 1. By definition, it's going to be the electric field dotted with the area, and you do an integral, right? Let's go equals. Okay. The dot product. What's the electric field?
E naught over 2.
E naught over 2 I hat. E naught over 2 and then I hat. And what's dA? Here the vector. It has magnitude dA, but in what direction?
Minus.
Yeah, it's in the I hat direction, but minus. So let me make my parentheses here. So minus. Right? So you have dA pointing to the left. Okay, that's dA. So now I need to E naught over 2, that's a constant, and then the minus sign. So I have this minus E naught over 2. And then what's the dot product of I hat dotted with I hat? I hat with I hat is 1. Yeah. If it were I hat and J hat, they make 90 degrees, that would be 0. In this case, I hat and I hat, they make a 1. Their dot product is 1. So what's left inside the integral? Just dA. Good. What's the integral of dA? It's a. So minus E naught over 2 times A. That's the first one. Okay. Next one is here. We're going to, again, apply this definition of flux to situation number 2, to case number 2. By the way, the area of all of these, it's the same surface, same area. All of them, they have area in it. So here it is. For case 2, we're going to call it flux 2. By definition, it is E dot dA. Like so. Equals sign. What's E? E naught times I hat, right? Okay. E naught times I hat. Dotted with dA. It has magnitude dA, but what's the direction? Not quite. The area is pointing this way. Huh? It's in the I hat and J hat, right? In this kind of. So it's in the N hat direction. It's in this direction, N hat. Okay, so we'll just call it N hat for now. We'll worry about what it is in a second. So I have E naught just comes out of the integral. And then I have my dA. And then we have this I hat dotted with N hat. Okay? I hat dotted with N hat. The dot product of two vectors is the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. My two vectors are I hat and N hat. Both of them have a hat. So what's their magnitudes? So what's the magnitude of I hat? One. One, right? It's a hat. It's a unit vector. So it has size 1. So I hat has magnitude 1. How about N hat? 1. So it would be 1 times 1 times the cosine of the angle between them. It's going to be this. E naught, dA, and then we said 1 times the cosine of the angle. What's the angle that they make between each other? Here's I hat, here's N hat. Somebody said 30? Yes. It's this angle, right? I hat points to the right, N hat points this way. So if this is 30, this would be 60, therefore this one would be 30. So it's 30. So cosine of 30.
Was that all the lines supposed to be vertical?
Which one? This one? Yeah. Okay. And then what's cosine of 30? 3 over 2. And then you got E naught. And then it would be the integral of dA, which is? So we could have done it, we could have just said it's EA times the cosine of theta. So E times A times the cosine of the angle between them, which is square root of 3 over 2. That's the shortcut. I'll lower the board, I'll erase my electric fields here. They're supposed to be to the right still. For case 3, in what direction is the electric field? Okay. To the right. In what direction is the area? Up. It's meant to be vertically up. So what angle do they make with each other? 90. So how much is the flux?
0.
Yeah, nothing goes through the area. So here's the area. Think of it this way. The field just passes this way. Passes by, not through. So the flux is just 0 for this one. No calculations are needed. 0. Next one. Next one. What's the? In what direction is the field? Well, to the right. In what direction is the area? It's in this N hat direction, right? The area is in the N hat direction. You're told this angle here, yeah, that's the vertical. That's 30 degrees, right? Yeah, so what would this angle be? It's going to be 60, yes. That angle is going to be 60. Because if this is 30, what would this angle be? That's 30, they're vertical angles, right? So that's 30, this is 30, and if this is 30, this has to be 60, because they make 90 together. So this is 30, this has to be 60. So it would be just the electric field, the magnitude of E. So the flux for the fourth case is going to be the magnitude of E times the magnitude of A times the cosine of the angle. I'm not going to go through the integral again, because it's going to give us the same result. So it's going to be the magnitude of the electric field. What's the magnitude of E? So in magnitude it's just 2E naught, right? Magnitude. Magnitude of the area is still A, and then cosine of what? 60 degrees. Cosine of 60 is a half, so it's going to be E naught A. Say that here. We're going to do more. Okay? So we need to get familiar with the concept of flux before we get to Gauss's. Yes?
So flux is always a scalar? It's never a...
Flux is a scalar, yeah. Could be positive, negative, or zero, but it is a scalar. No direction to it. Yeah. Yeah. Because we did it a couple of times, and we always ended with just magnitude of E, magnitude of A times the cosine of the angle. So I just basically said this will give us that. Yeah. All right. The next example, or two examples, two more, and then we'll go to Gauss's. They're here. Again, ignore 4, we come back to it. Square it like 3 down.
We would only have to simplify like that if the area of the key is.
Yeah. If the both the area and the electric field are constant. So in this case, the area is constant, the electric field is constant. So, got this one here. Let me read it. You have two cylinders. They're closed cylinders. And they're put in an electric field. By the way, the cylinder, the area on the right side is A, and the area on the left side is A. It's a cylinder, so right and left, they have the same area. So A and A on either side. This cylinder, the top one is longer than the bottom one. Okay? And they have the same area. It just happens the bottom one is short. Okay? The length of the bottom cylinder is short. The electric field is not uniform. It increases from left to right. So the electric field, let's say, on the left side, let's say, is magnitude 1. In the middle, maybe it's, let's say, 5. And on the right side, it's 10. Okay? So let's say it increases as you go from left to right. So here, maybe, again, 1, 5, 10. Okay? Just think of it like that. 1, 5, 10. The question is, which cylinder will have a larger net flux? Larger net flux. So I am going to, here's my cylinder. Before we answer it, here's my cylinder. And it's a closed surface. So there is an inside and an outside to that surface. So the convention is this. In what direction does the area point if it's a closed surface? It's a closed surface, here's the convention. The area vector is always perpendicular and away from the surface. So for example, here's the surface. So this end is flat. So in what direction is the area of this end? That way. And because it's flat, the area of every bit here just points down. How about here? Exactly. Okay. To your left. And then how about here on this curved end? At the top, it's like this. How about here? Like that. So it's radially outward. Okay. So it's radially outward on the curved end. The circular end is radially outward. Let me put the cylinder maybe this way. So it's always perpendicular and away from the surface. So it depends on where you are on the surface, the perpendicular will point in different directions. And like when it's flat, it's just one direction. Just away. All right. Actually, let's keep it this way so it doesn't fall. Let's look at the top cylinder. We said the area on the left side will point in what direction? Left. And the electric field is to the right. So the flux is positive or negative from this side? Negative. How about from this side? Yeah, the area is to the right, the electric field is to the right, so the flux is positive. In total, is the flux, oh, how about the curved end? How much is the flux? Zero, yeah. The area is pointing radially outward, the field passes this way. No field is entering through the side. So there is no field entering through the sides. So is the net flux positive or negative in this case?
Positive.
Positive because the electric field on the right is greater value, right? Remember we said maybe this is, let's just think of it as 1, 5, and 10, okay? Just give it some values. So on the right side, let's say you get a flux of magnitude 10 exiting. On the left side, you have a flux of magnitude 1 entering. So in total, what's the total flux? Just none. Let's look at this cylinder here. The flux here will be positive or negative? Negative, because the area points left, electric field is entering. In here, the flux is positive. So if the flux here is 5 entering, here it's 10 exiting, so what's in total? What's the total? Just the 5, yeah. So which one has the larger net flux? So the answer is the 5.
No, wait.
Yeah.
Sorry, what's the reason?
For what?
What's the reason that the longer cylinder has more flux? What's the reason? Can you like repeat?
You see the electric field? The electric field on the left, from left to right, is increasing, right? So we're told the electric field increases in magnitude from left to right. So, and I said let's give specific values. Let's say from this end, let's say the electric field has value 1. In the middle, let's say the electric field is value 5. In here, the electric field, let's say, has value 10. Just to come up with something. So I ask you, the flux here, is it positive or negative? Negative because the area left, the electric field is right. So let's say it's a negative flux of -1. Okay, that's entering. On the right would be positive flux, right? So, and it would be, let's say, positive 10. So what's the total here? What's the net flux? 9. Yeah, so a net of 9. But here, you get 10 exiting, 5 entering. So the net is just 5. Does that make sense, everyone? So when it's entering, it's considered negative. If it's exiting, it's considered positive. It would be consistent with our notation for, with our plus and minuses. So think of, if you have a negative charge inside your cylinder, think of, if you have a negative charge in a cylinder, would you have a net flux that enters or net flux that leaves? So imagine you have a cylinder and you put a minus charge inside the cylinder. Will the flux be entering or leaving? Yeah, flux would be towards the minus charge. So yeah, it would be, the net flux would be entering, and if flux enters, it's negative. But if you place a positive charge, the net flux would be exiting. That's what Gauss's law changes. So we're going to come back to that. Okay. So that, most of these are conceptual. We want to get some specific to some numbers here before we make a statement of Gauss's law. All right. I'm going to go to this one. So this, what's this problem? So let's, first of all, let's ignore the middle. That's why I wrote it. You have a plate, 100 centimeters, 100 square centimeters, this plate. And this plate is also 100 square centimeters. So I have a parallel plate, right? And call it a parallel plate capacitor, right? That's what we called it last time. And let's say this one has a positive Q and this one is minus Q, meaning this one is positive 5 nanocoulombs and this one is minus 5 nanocoulombs. The first question is, what's the electric field in between them? Okay. And we're going to say, basically, assume it's basically the plates are so big that they're basically infinite. Okay? So we're going to use the approximation that you have two infinite sheets. What's the electric field between two infinite sheets?
Sigma equal to epsilon.
2 or 1 epsilon
Oh,
naught?
1 epsilon.
Yeah, if you have one of them, it's sigma over 2 epsilon naught. But in the middle, remember, both of them point in the same direction, so it's sigma over epsilon naught. So that's that. Okay. Now, what is sigma? How do you get sigma if you have Q?
Sigma times the distance. Charge over the
It's not-
Charge over area. Shoot, divide by
Yeah,
R.
so remember, lambda is charge over length. Sigma is charge over area. Yeah, so it is the charge over the area. And then you get your epsilon naught. So now you will substitute your numbers. So you have E. The charge is 1 nanocoulomb, so 1 times 10 to the minus 9. Not 1 nanocoulomb, sorry, 5 nanocoulombs. Epsilon naught, you should remember this value by now, right? 8.85 times 10 to the minus 12. The area is 100. But is that good, or we need to change it? Change it to square meters, right? So multiply by 10 to what power? Yeah, -4, because from centimeter to meter it's 100, but you have to do it twice. So just do that, and I will quickly check my answer. I have 5.65 times 10 to the 4. What are the units of the electric field? A charge is coulomb.
Everybody.
Newtons per coulomb? Correct. Newtons per coulomb.
If the 1 centimeter squared was like 5, where would that show in the equation? Or,
We didn't get to that part yet.
oh,
Yeah, so, it says here, a 1 centimeter square is placed between the plates, right? We haven't placed it yet.
okay.
We're going to do that next. Yeah. So this is the electric field, right? So now, to the 1 centimeter. Here's the 1 centimeter. Let's say the eraser, I pretend it's 1 centimeter, it's not, it's more. But here's 1 centimeter, we're going to place it here. But they say we're going to place it in such a way that it will make a 45-degree angle. So I'm going to place it this way. So if I place it this way, it will experience the maximum flux, right? Agree? If it's this way, all the field will pass through the surface. But if it's this way, only part of the area is available for it to pass through. So we're going to place our 1 centimeter thing here. So the unit normal is going to be like this. And the electric field will pass by, right? So the area makes 45 degrees. So what's the flux through this 1 square centimeter? What do we do? You can go to the integral, but you don't have to. You can, everything is constant, so we just go here. only the magnitude of E, magnitude of area, times the cosine of the angle between them. So the flux would be EA cosine of theta. E is 5.65 times 10 to the 4th power. 1 centimeter, so you multiply by 10 to the minus 4 to get square meters, and then cosine of 45. 10 to the minus 4, 10 to the 4. It turns out to be about 4. Newtons meters squared per coulomb. Flux is electric field times area, so the units would be electric field is newtons per coulomb, so you have to multiply that squared. So that's the flux. Now to the statement of Gauss's law and its applications. So we're going to state Gauss's law, and then we'll talk about its applications. It's a law, so we're going to take it as, it would be one of the laws that we will learn this semester about electromagnetism. Specifically, there are 4 laws called Maxwell's equations. One of them is Gauss's law, and then there will be 3 more. So this is the first one. In ways, it's equivalent to Coulomb's law. So in fact, I will show you how to get Coulomb's law out of Gauss's law. I'm going to lower here. And if you're wondering, all the problems here, they're in the lecture notes, so feel free to check them out. So, to Gauss's law. We're going to write it down. It's in mathematical form. It says the following: the flux through a closed surface. Or a closed surface. So how do I say a closed surface? Well, the flux is this: E dot dA. E dot dA. So how do people? This is E dot dA. That's the definition of flux. All the surfaces we have used, basically, for the most, except for the cylinder, they have been open. So how do I say closed surface? Yeah, you put a circle on the end. So closed surface, people use this notation. That means closed surface. Okay. So this is part of the law. This is the left side of the law. It says this: the closed surface integral, right? Any surface is equal to this: Q enclosed over epsilon naught. Sometimes in my notes you might read Qn. Enclosed or n. So it's the charge within that surface. Okay? It says this: E dot dA over a closed integral over a closed surface is always equal to Q over epsilon naught. And I'm going to do a